Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so welcome everyone. Today we have Nathan Weeb visiting the Quark group. He's a candidate for a researcher position in Quark. He's currently a postdoc at the Institute for Quantum Computing at the University of Waterloo. And today he's here to talk to us about progress towards a killer application for quantum computation. So Nathan, thank you for coming.
Great. Thank you very much for the introduction, Krista. So, as Krista said, I'm going to be talking to you today about the quest to find a killer application for quantum computation. So, the idea for this talk came from a question that was actually asked to me by two different colleagues at two different conferences. And this question is, if I was given a quantum computer with 100 qubits in it, what would I use it for? And this question got me thinking and made me wonder whether we've actually found something that realistically is a killer application for quantum computation yet. And if not, what such an application would ultimately look like. Now, the notion of what a killer application is to some extent sociological. It depends on what problems you think are interesting or what problems you think other people find interesting. So in order to preface the opinions that are contained in this presentation, I really think it's necessary just to spend a moment talking about the sorts of research problems that I personally find interesting. So my research touches a whole bunch of different areas involving quantum simulation, adiabatic quantum computation, quantum algorithms, numerical analysis, foundations of physics, and Bayesian inference. So it might come as a bit of a surprise, given this, that to me, my vision of a killer application looks something like this. This is VisiCalc, a program that is widely regarded to be the first killer application for home computers. This simple application single-handedly justified the purchase for many people of a very expensive home computer in 1982. So, from my perspective, something that ought to call itself a killer application for a quantum computer should spark people's imaginations at least as much as VisiCalc did. And if it doesn't, then I would not consider that to be a killer application. So, in this talk, I'm really going to put candidates forward for potential killer applications, and then discuss whether or not I feel that these are adequate or whether they're close to being killer applications. And these two candidates that I'm putting forward are quantum simulation and quantum data fitting. The outline of my presentation for the simulation will involve an introduction to quantum simulation, and then I'm going to present a new method based on non-unitary simulation that was developed by myself and Andrew Childs that improves upon existing methods used in, for example, quantum chemistry simulations. And then I'm going to discuss data fitting. In particular, I'm going to give an introduction to the linear systems algorithm on which the data fitting work is based, and then I'm going to present the algorithm. After which, I'll conclude and discuss whether either of these actually is a killer application, and if not, how close we are. So, quantum computation really began with thoughts from Richard Feynman and Manin that suggested that quantum information could be stored and manipulated in quantum systems themselves. Now, this actually doesn't sound on the surface like all that deep of an insight. After all, Moore's law has caused us to miniaturize to get components smaller and smaller. So this sounds like it may just be a replication of the same theme, just smaller. But actually, it's a fundamentally different idea. The reason why is because of the fact that the information has to be stored in a manifestly quantum fashion. That is, in a way that defies a classical description. So the way that this is generally done in quantum computation is that we have bits that then are generalized into quantum bits or qubits. And unlike classical bits, these quantum bits can be an arbitrary superposition of 0 and 1. So the difference between this and maybe a full analog computation, one of the differences at least, is the fact that when you measure this, you get a discrete outcome. So every time you measure the quantum bit, it probabilistically will either be 0 or 1. And the probabilities depend on the amplitudes of A and B. You can, of course, repeat the same idea with more quantum bits. So with 2 quantum bits, your system can now be in an arbitrary superposition of 4 different values. And obviously, if you imagined you had 3 qubits, then it could be in an arbitrary superposition of any of 8 different possible combinations of 0 and 1. So that's how this works. And of course, a quantum computer also has to be able to transform these quantum bit strings, at least in principle, into any other possible quantum state within the quantum computer. So the question is, where does quantum computing potentially get its advantages over classical computation? And there's many different candidates that one could use for this, but to some extent, one of the biggest things is this exponential growth of the size of the amount of information that's required to represent the quantum state. So to give you an idea about how these exponentials end up scaling, I've given the following diagram. Imagine that you had a single quantum bit, and you could write down all the information you needed in order to represent that quantum bit within some fixed error tolerance on a single grain of sand. Then, of course, the relevant unit is, well, how many qubits would you need in order to make a pile of sand the size of a Tyrannosaurus rex? And that turns out to be 48 qubits. If you want to look at a quantum computer that has twice as many qubits, 96, then the pile of sand that you'd need to represent that quantum state would have a volume of about a small moon. Going up, again, a factor of 2, that pile of sand would have to have this size of a small planetary nebula. So obviously, this problem that I began with, this question of what I would do with a 100-qubit quantum computer, this is not a trivial computational device. This device would require a lot of classical information in order to specify what's going on inside the system. So you ought to imagine that quantum computation should be useful for a host of different problems. And a number of algorithms are known for which speedups over the best known or best possible classical algorithms exist. And of these, I'm going to focus only on those that offer superpolynomial or exponential speedups. The reason is that, obviously, we really want something that is much better than a supercomputer. So of these, there's a number of examples. And the 2 that I consider most promising are, of course, quantum simulation and linear systems algorithms. And I'm going to be discussing those in detail later on. So let's start with quantum simulation and the quantum simulation work that Andrew and I have done. So the idea of quantum simulation is actually really straightforward at its core. What you have is you have a quantum computer, which intrinsically is a quantum system. And you have the ability to perform arbitrary transformations on the quantum state inside that quantum system. So in principle, other physical systems are themselves quantum systems. So you'd imagine that the transformations that naturally, say, a chemical system is undergoing could be performed on a quantum computer on a logical level. Similarly, the quantum transformations that occur in condensed matter systems ought to be emulatable by a quantum computer of an appropriate size. And this is the idea. You basically use the fact that a quantum computer is a universal device to emulate the natural quantum evolutions that exist in other systems. And you can actually do this efficiently, whereas on classical computers, there's no known way in general to simulate arbitrary quantum systems efficiently. So you could do some kind of amazing things if you were able to get a 100-qubit scale quantum computer. You'd be able to simulate reaction dynamics and learn spectral properties of chemicals without ever having to synthesize them. You could use these devices in order to investigate models for exotic superconductivity or look for quantum phase transitions in certain condensed matter systems. There's many different possible applications of hard problems scientifically that quantum simulation could be used to address right now, and important ones too.
Wouldn't there be some questions that you cannot answer in a regular, ordinary way, even with the ability to synthesize stuff?
So what do you mean, sorry?
You said you can answer some questions about chemicals without synthesizing them.
Right.
But I would imagine there are some questions that you cannot solve even by synthesizing these chemicals.
Right. Like, I was specifically referring to spectroscopic properties. Obviously, if you synthesized it, then you could just throw it through whatever spectrometer you wanted and looked at that. But you couldn't get information, say, about reaction dynamics or maybe more sensitive pieces of information from it. So one of the key things that you can do with quantum simulation is that actually, if you do this on a quantum computer can perform error correction, and it can actually certify that the answer that you get out of this quantum simulation is actually valid. So that's one of the very neat things that you can do with quantum simulation you may not be able to do with other approaches to try to build analogous experiments, say, to one of these systems. And also, the number of logical qubits that you need in order to equal or exceed the power of a conventional supercomputer isn't very big. You only need something on the order of 40-ish qubits in order to start getting to the regime of existing supercomputers. And also, unlike many of the other quantum algorithms that have been proposed so far, this family of quantum algorithms solves a host of problems that scientists actually care about deeply right now. And a lot of processor time is spent currently on solving these sorts of problems.
Can you clarify what you mean about error correction and certification? I guess, or maybe you can give me an example of what you mean by that.
You know what? Actually, the next slide it probably gives me a better prop for describing this. So, yeah, sure, Matt.
Maybe this is what maybe you're going to talk about this in a bit because you said you're going to talk about an algorithm of yours. But two steps. I was curious when you mentioned simulating small molecules on a computer. The first question, on a quantum computer, we can simulate time dynamics, but we might be interested also in having to cool the molecule to its ground state before doing the time dynamics, and this might put an overhead that we need extra bath qubits. And
well, there's several ways. Technically, actually, there's no overhead with bath qubits that are required because you can always, in principle, simulate an adiabatic evolution to cool it into its ground state, and you don't require any additional qubits for that. The bath, for the question about the bath, worst case scenario, you require one additional qubit. You can effectively do a Fourier single qubit phase estimation algorithm and use that to cool it.
And then a separate thing is whether you might try to do, I'm just wondering how you're going to encode the Hamiltonian, because 100 qubits is sort of, in terms of a spin system, that's great. That's like 100 spins. But in terms of a system of electrons, that's not actually that many degrees of freedom. If you have 100 electrons, that's not all that big of a molecule.
Sure. I mean, this really depends on the way that you're doing this. And for example, if you're talking about simulating a quantum system in some first quantized form, then the way that you would have to probably encode that is you would begin by saying, okay, well, the electron cloud is distributed according to, say, an s orbital at the beginning of that, and you'd encode your information efficiently with that. And then you would require a quantum algorithm to prepare the initial state as an s orbital and then evolve in first quantized form. That, of course, isn't terribly efficient. A more efficient way of doing it is to, if possible, map it to a second quantized form and use creation and annihilation operators to deal with that. Then you only just have to abstractly mention the state at the beginning of the algorithm that the electrons are in.
Sure, I'm just wondering, maybe we can talk about this
in
terms of first quantized, second quantized. The Hilbert space of 2 to the 100 it sounds huge, but at the same time, when you ask, how many orbitals electrons can have, and you count the number of possible spaces for even a fairly small molecule, it's already getting up around there too.
Even in second quantized form, you only get 50 orbitals at best. You still need to loosen things off for phase estimation.
Exactly.
So that's the size we can still do classically.
Right. So I'm wondering.
You're on the limit, on the edge, but you really, the number I tend to wind up using is a good 200 at least. Because now you're beyond what you can do classically in any length of time.
Yeah. For these sorts of 40 to 100-ish qubits is certainly for spin systems going to be where sort of the state of the art is, I think. Whereas, there are certainly overheads that come in with the chemistry simulations, but we can discuss that later. So going back one more on the stack to the question about the certification and why I was bringing that up. One of the big trends in experimental physics these days is to look at so-called analog simulators. And this is justified by the fact that building a full quantum computer seems to be a very difficult thing to do. But quantum mechanics is just something that happens naturally in the lab. So why not just construct a gigantic lattice of hundreds of interacting atoms and call that a quantum simulator? Well, it is quantum, and it is simulating something. But the question is it simulating something other than itself? And can you actually, if you want to use this in order to answer a computational question, what do you need to do? In this case, certifying this system of several hundred qubits that was taken from the ion trap group at NIST, what you need to do, at least on a naive level, is you need to first understand what the state is, and that may require tomography, which is going to be exponentially expensive. So there's no known way of getting these sorts of simulations, which are already very complicated and very sophisticated, to actually solve genuine problems. So that's one of the reasons why I emphasize the certification issue, because, you know, there's this false dichotomy where you say, this digital simulation experiment that people have done is only 6 qubits. Why are they bothering when you can do a few hundred qubits? Well, the reason is because to some extent you can trust what the output is of these sorts of experiments, whereas with this one, who knows?
I see. So what you're saying is because you can break a quantum computation up into very small parts and then into an algorithm, then you can certify it, rather than having a large system that you just say does something.
You just pray that according to your understanding of the laws of physics, that it ought to be the system that you think it is.
Just as a side note, Bert and I have been looking at tomography as a killer quantum app. That's a possibility.
That's
actually the circuit model.
I'm going to get to that point with my data fitting algorithm later. Cool. So that's enough said. So let's talk about basically how this emulation process inside a quantum computer actually works out. So there's several steps. The first thing is what you have this quantum system, and this is the thing that you'd like to simulate. And you have your quantum computer, which is the device that you're using to simulate it. In general, you're going to require more qubits for your quantum computer than the quantum system, but for spin systems, it turns out they can actually be the same size often. So the way that the algorithms begin is you want to simulate the evolution of some initial state forward in time to a final state in the actual quantum system. You begin by taking that state and encoding that as a qubit state inside your quantum computer that's logically equivalent to the initial state. Then this continuous time evolution that you would see in the physical system, you approximate via a series of discrete gate operations, which map the system to a final state. And that final state ought to be logically equivalent to the evolved state up to some error tolerance. And that's how these algorithms fundamentally work. And if you design this right, then you'll be able to know beforehand what that error can be in a worst case scenario. So unfortunately, this isn't it, because getting the final state as the outcome of this thing is like getting a fortune cookie that contains the answer to all of life's problems in it. It doesn't really mean too much until you extract information from it. So that final quantum state that you get here, it doesn't solve any problems. What you have to do is you have to measure that, which destroys the state, and then start the simulation protocol all over again to get more information. And repeat this potentially a large number of times in order to learn the information that you wanted about that quantum system. Yes?
So concerning certification, since quantum computer makes errors as well, so be careful about true certification. Now, a priori, it's not obvious that this is better than just testing many times the quantum system, if testing is available.
You know, if testing is available, like let's say you actually have the quantum system, you're entirely right. Because of the strong analogy between the quantum computer and the other system, yeah, why not? If you've got the actual system, the very best simulator of that system is the system itself. If you want to learn something about it, just experiment on it. But the problem is, you don't often want to use simulation in order to understand a physical system. What you want to understand is you want to understand a mathematical description of a physical system. And that's what a quantum computer can do. A quantum computer can say that if you designed this simulation algorithm properly, then the mathematics that describes this time evolution should be simulated accurately by the quantum system.
You can also ask questions you can't do in the physical system.
Yes, and that's the secondary benefit. There are certain experiments that would at least be impractical to do in a physical system. So I'll just do a very brief example of a spin system type problem, just to understand, just to give you an idea about how the simplest variants of these quantum simulations work. So this is a model known as the Transverse Ising model for two interacting spins. It's a model used in condensed matter physics to describe quantum magnetism. And the basic matrix you could just imagine is a 4x4 matrix that has an interaction between the Z components of these two quantum spins, and also it has an interaction with an external magnetic field that's pointing in the x direction. So if you want to simulate that, then it boils down to the question of how do you end up taking this quantum mechanical time evolution operator, which generates, say, this transformation, into a series of gate operations on the quantum computer. And well, in this case, I guess it's a 4x4 matrix, so you probably could do it directly. But in general, for higher dimensional systems, it's hard to actually synthesize this in a straightforward way. So the way that this is done is using a Trotter decomposition. So the idea is that this Hamiltonian is the sum of three terms. Each of these, it turns out, can be efficiently implemented on a quantum computer. But together, it's not clear how you would do it. So what you do is you say, OK, well, we break up this time evolution into a series of very short time steps. And in each of these time steps, you will evolve only according to one of these three terms. And by increasing the number of time steps, you can make this approximation arbitrarily accurate. So if you do that, you can actually find a quantum circuit that's equivalent to these three operations. And this quantum circuit is down here. But unfortunately, this isn't done, because there's actually two halves of these sorts of simulation algorithms. The first half is what I've described here. It's this process of Trotterization and breaking it into elementary rotations. And the second half is converting or compiling these elementary rotations into fundamental gates that the quantum computer can actually use. And these gates, there's a number of different gate sets that can be chosen, but common choices are pi/8 gates and the Hadamard gates. There's many methods that are known to synthesize these single qubit rotations that appear in this sort of a circuit. And of course, the group at Microsoft Research are world leaders on these sorts of techniques. Now, let's talk about what the sort of state-of-the-art methods are at present in quantum simulation. The most common approaches that are often used are these product formula approaches, which are exactly the same sort of thing that I showed you with this example of the spin system, just more sophisticated. They often will use higher order Trotter formulas than the one that I presented. They're very good for high accuracy simulations of extremely sparse Hamiltonians. More recently, methods based on quantum walks have been developed, largely by Dominic Berry and Andrew Childs. And these methods are, unfortunately, they are not as good for high accuracy simulations, but they are much better for non-sparse Hamiltonians. The methods that I'm going to be discussing in this are multi-product based methods, which actually are superior to these product formula approaches in almost every way. And I'm sure the group will be able to tell me very quickly what the one way they're not superior is. But I'll leave that as a surprise. So with product formulas, the best known result for the scaling of product formulas is this. Here, M is the number of elementary Hamiltonians that you have in your Hamiltonian. Again, the Hamiltonian is like your quantum energy operator. So it scales like quadratically with the number of elementary terms that you have in your Hamiltonian, and it scales nearly linearly with the norm of the Hamiltonian times the evolution time.
So little h is the norm of each of the capital H sub j?
Yeah, it's the maximum norm of all of little h sub j's. So m times that will clearly be an upper bound of the norm of the Hamiltonian.
H sub j, are they supposed to be in some certain way non-interacting with each other?
Oh no, they can interact with each other. But the point is that each of these individual terms have to be individually simulatable. Okay, so they don't necessarily have to be non-commuting. So the final thing over here is the error tolerance. And these algorithms scale subpolynomially with the error tolerance that you want out of the simulation, but unfortunately not polylogarithmically. So that's the basic intuition behind this. And in order to get this sort of performance, you can't just use the basic Trotter formula that I showed previously. You really have to choose higher and higher order Trotter formulas as the evolution time and the error tolerance end up becoming more stringent.
What's big O with tilde?
Oh, big O tilde. What I've done is I've dropped terms that are logarithmic in here, and not really, just to make the expression look nicer.
So it's like multiplicative logs.
Yes, multiplicative logs.
Why are you saying this is subpolynomial? This
Oh.
looks...
Okay. The reason why is because obviously if I didn't have this this square root here, it would just be like e to the log 1 over epsilon. So that would be, log 1 over epsilon. But when you have the square root on here, this actually makes it smaller than any polynomial function. So that's why this is a subpolynomial. So the basic intuition for how you generate these high-order Trotter formulas is like this. Say you have your time evolution operator, and what you want to do is you want to write this as a product of elementary time evolutions that you can actually carry out. And you want to choose the times for these elementary evolutions so that you reconstruct the Taylor series of the actual time evolution operator within some pre-prescribed error. And so this is actually a hard task, to try to find all of these different times that are necessary in order to actually reconstruct the Taylor series. So there's actually a cottage industry in numerical analysis for finding different times in order to do this. However, there's fortunately a very nice recursive scheme that Suzuki invented in order to refine a low-order approximation into a higher-order approximation. And this iterative scheme basically works as follows. You start with a low-order approximation, and you do 2 time steps forward with that low-order approximation. Then you do 1 time step back for a certain value of the time, and then you do 2 more time steps forward. And with this 2 forward, 1 back, 2 forward procedure, by choosing this single parameter rather than all of these different parameters individually, you can actually find a neat way of guaranteeing that you'll increase the error by 2 orders by doing this, at the cost of increasing the number of terms in your approximation by a factor of 5. So the trade-off is you have 5 times as many exponentials, but you get 2 more orders of accuracy out of doing this.
Can you elaborate on that O term?
Sure.
Does t tend to 0
Okay.
in some way?
This is it. Yes, it does. So here what I'm doing is I'm just talking about analyzing one of the short time slices for the time evolution. If you're looking at a long time evolution, then imagine just taking r slices of that and making each of them short, and then you use one of these high order approximates.
So the
for that.
slice is tiny, but it also gets partitioned some more. in this.
Yeah, it gets partitioned some more into these smaller bits out here. And so I'd just like to give you guys a visual way of understanding how these product formulas work, because our approach, in contrast, is going to do something very different. So here, these boxes, what they do, this represents a Taylor series. This first box is a 0th order term in a Taylor series for the time evolution operator. This is the first order, this is the second order, and then these two have errors in them. And what the Trotter-Suzuki formula does is it combines them in an appropriate way such that when you multiply these boxes together, that these errors over here end up getting a negative sign because of the fact you're looking at a backwards in time evolution. The products between all of these end up causing these terms to interfere with each other and cancel out. And a symmetry consideration ends up causing these higher order terms to also cancel out when you put it in this form. And so that's basically how this works. One of the big drawbacks, though, is if you just take a look at what happens with the errors whenever you multiply, is that every time you multiply, new types of errors are created by multiplying terms that previously worked with error terms. So for example, let's take a look at the error terms that, like the second order error terms here. These can actually be formed by multiplying this correct term, or error terms of that scale can be formed by multiplying this correct term by that incorrect term. And thus you'll generate a more complex set of errors through multiplication than you would otherwise. So a lot of the effort you can imagine conceptually in the Trotter-Suzuki formulas is to actually counteract these errors that are introduced by multiplication and deal with the fact that multiplying polynomials isn't a very natural way to build a Taylor series. The natural way to build a Taylor series is to add them. And that's exactly what we do. So we suggest doing something very different. Don't multiply. Start with your lower order formulas. Come up with some weighted sum of these lower order formulas, and you add them together in an appropriate way to make the Taylor series you want. And this is very natural because, of course, with Taylor's theorem, you just add the individual terms in the Taylor series expansion to construct it anyways. So this doesn't create this problem of propagation of errors. This sort of an approach has already been known in the numerical analysis community for quite some time. The Richardson extrapolation is the simplest example of these sorts of approximation building methods. And in general, we can construct multi-product expansions that work by adding together many low-order product formulas together with different coefficients out here and construct our approximations that way. And that's the method that we use here. So rather than these massive product formula approximations, we add together a bunch of them with different coefficients in order to approximate the time evolution operator within some accuracy. And so there's some advantages to doing this. The first key advantage is the number of exponentials that you need to create the formula using a Trotter-Suzuki, you notice, will grow exponentially with the order. And that's exactly for the reason that I mentioned. Every time you increase the order recursively, you need 5 times more exponentials, hence the 5 to the k minus 1. Whereas with the multi-product formulas, you only end up needing order k squared terms, which is fantastic. But of course, there's something that's very unfantastic about this as well. And that's the fact that although the Trotter-Suzuki formula is unitary, which means that it's an ordinary quantum transformation that can easily be done on a quantum computer, these formulas in general are not unitary. So you have to go through a greater effort on a quantum computer in order to try to synthesize them. However, we end up discovering ways to do so and actually find, surprisingly, that you can use non-unitary operations on a quantum computer to simulate unitary dynamics more efficiently than you could by using the unitary dynamics by itself. So the way we do this is using the following circuit. This circuit is designed in order to create a linear combination of 2 different unitaries. So it just effectively sums 2 unitaries with an arbitrary coefficient kappa in front of it. And the way you do this is you take this single qubit quantum transformation here, you apply it to the input bit, and perform these controlled evolutions, where here U0 and U1 you could think of as just 2 different operator splitting formulas. This one might take 1 time step, and this one could take 2 time steps, but they're the same formula. And if you measure this and observe 0, then you'll have actually performed the correct linear combination that you want. Whereas if you measure 1, then you won't, and you might have to perform some error correction. This can also be generalized pretty straightforwardly to adding more than 2 terms, just by using a larger unitary on many qubits. And that's effectively what we do, but for the purposes of this presentation, I'll focus on just the adding 2 terms together because it captures all the intuition you need.
So I have a philosophical question. The non-unitarians here, right, actually needs to be understood as a loss of information on the business qubit side, right? So how big is the loss of information, and why do you think that the retained information is sufficient?
Well, sure. The actual qubit it remains in a pure state, actually, during the entire evolution. The reason why is because when you take a look at this linear combination of unitaries that you end up getting over here, this is actually just going to map a pure state to a pure state. So it's not like you're going to end up getting a mixed state out of this linear combination. For example, let's take the worst possible, most destructive linear combination that I can imagine for these sorts of things. Imagine you want to do a linear combination of identity and Z. What you end up getting is just a projector onto the 0 state from that. And that just ends up mapping you to a pure state. So these sorts of combinations will always end up giving you a pure state. Yeah, sure.
No, one more back.
One more back? Okay,
Yes.
certainly.
So, in cases that you deal with, what is the probability of getting 0?
Okay. The cases of probability that I deal with, it depends on the operation. And the reason why, I'm going to get to this in a second, but there's two sorts of errors that end up happening. It depends if UA is U1 is approximately U0 or approximately negative U0. Those are the two cases that come up in the simulation algorithm. And in one of the two cases, it turns out if an error occurs, it's entirely easily correctable. In the other case, it's catastrophic and you have to throw out everything. So much of the cost of this algorithm is actually going to boil down to making sure that the probabilities of these catastrophic events occurring are vanishingly small. But for the non-catastrophic ones, the probability of success is about 0.5 is what we found the optimal to be.
And what are U1 in
Okay,
general?
in general, U0 and U1 are going to be two different values of the same. Let me go back for a second. This is what it is. Sx over here is an approximate for the time evolution operators. So it's going to be one of these product formulas. So in general, these are all going to be of the same form, but they're just going to use a different number of steps. So one of them will be the formula that two copies of the formula with half the time, and the other one will be like one copy of it with a full step. So they're going to be exactly the same form of approximation. It's just one of them will involve many steps, and one of them will involve maybe few.
For the same Q or different?
For different values of Q here.
Different.
Yeah.
So maybe you said this already. What do you get if you measure 1? I
Okay.
mean, maybe.
You know what?
Against error.
You know what? How about I go to the slide? All right. So if I go to the slide, if I measure 0, then what I get is I get the linear combination of the two unitaries that I want to actually implement. If I measure 1, then I get the difference between those two. And so this is one of the reasons why I mentioned it depends on whether or not the two are close to each other or very far from each other. Because if they're very close to each other, then this term will be approximately 0. And if it's approximately 0, it's just going to clobber your state, and you're going to get some garbage left over. Whereas if you have if they're opposite to each other, then you'll have approximately 2UB, which is a unitary operation. And furthermore, it's a simple unitary operation you've got an operator splitting formula for. So you can actually invert that. And so that's the basic intuition for this. So for some of the steps, it'll be catastrophic. Some of them will be good.
But typical probability about 50%.
Typical probability is about 50%. Yeah, that's the best to shoot for.
But even if you are, do not collapse here, right?
Yeah.
Did you imply that it's actually projecting in a lower dimensional subspace somehow?
Well, I mean, what do you mean by that?
You're removing the first qubit.
You're just removing the first qubit.
By measuring it. So
Yeah.
the second is the one that you're one of the two.
Yeah, it's the second. The second is where all of the information that you want is actually encoded. This is just used in order to allow you to do this trick where you perform a weighted sum of these two. Okay.
So would you view this as a variant of distillation?
Perhaps. It's certainly along the same sort of theme. Yeah.
So a question related to whether it's like distillation. So you make this unitary transformation and it's bad. Okay, just draw it out and discard it. But perhaps one thing to do then, instead of trying to apply the unitary transformation to your actual state, you make an entangled pair, you apply the unitary transformation to half of it, and if it succeeds, then you teleport. So you do the unitary to your state, and otherwise you...
Yeah.
We try to recover from the other one?
Yeah, it's one of the things that I remember we looked at. We weren't able to get any traction on that particular idea to use, some sort of a gate teleportation type idea to do this, because that would clearly be ideal. But I'd be happy to talk about it later.
I guess the problem is that these are not Clifford gates that we're talking about.
Yeah, exactly. All right. So that's basically it. And as I said before, but now it's a belabored point, some of these are bad errors and some of these are not so bad errors. And just to give you a basic overview of how this would work for the simplest possible case, imagine what you have is you're just using this Richardson extrapolation formula here. In your simulation, you use this particular formula, and here, S1 here could represent the simplest Trotter formula you can use, the symmetric Trotter formula. So you use that formula with a weight of 4 here and a weight of -1 there, and you use those circuits in order to implement this particular linear combination. And again, in general, what will happen with this is that the error correction can be done with high probability in this case because S1 has opposite sign to that S1. Okay. So essentially how it works is as follows. The flow chart is you attempt a time step of one of those terms in here. You have 2 options. It either succeeds or fails. If it succeeds, go on to the next time step. If it fails, well, then you attempt error correction. And the error correction that you attempt, you can do using this exact same method. It turns out there's a chance of a catastrophic error when you attempt that error correction step, but that probability can be made arbitrarily small. So you attempt that, and again, if it fails, you abort the simulation. Otherwise, you try that time step again. And repeat this process until you're done.
Except you're doing this at every time step.
You're doing this at every time step.
And you could have, you know, a million time steps.
You could have a million.
One of them has a chance of a failure or abort.
Yep. The second last time step could be the one that fails. Nonetheless, when you consider all of these possible things that can go wrong and all the additional costs involved in making these errors small, you notice that what ends up happening is we end up getting an exponent up here which is smaller than the exponent that you end up getting for Trotter-Suzuki. Just because even despite all of this, these problems with error correction and the like, the advantages of these multi-product formulas are so great that you do end up getting a benefit out of it. This polynomially ends up reducing the scaling with the error tolerance over the best known results using just pure Trotter formulas.
That includes all the abort probabilities.
Yes. And so basically what this means is we've given a method that is superior to product formula simulation methods in nearly every way. Furthermore, this could lead to improved quantum chemistry algorithms. And also, most importantly, I think it gives a new way of thinking about simulation that doesn't directly involve a logical mapping between the initial system and the final system. The dynamics effectively that are going on in the quantum computer are actually not the same sort of dynamics that are going on in the physical system because of the non-unitarity. And it says that this paradigm has some advantages over the traditional paradigm. But the real question is, well, is quantum simulation a killer application? And I would say that for scientific computation, arguably you can say yes. However, for general purpose computation, probably not. Really, the golden standard of this talk is VisiCalc. And quantum computation is not something that is going to get people who are, say, interested in directly, quantum simulation is not going to get people who are interested in, say, data analysis to directly get out and be excited about quantum computation. So I don't think it's quite as compelling for general purpose computation, but undoubtedly it could be incredibly useful for scientific computation. However, the next thing you could think of is, well, maybe actually because you have such a compelling application for scientific computation, maybe it's possible that some problems within the scientific computation community or simulation problems can be mapped to other classes of problems that are more relevant. And this is exactly the same sort of intuition that's used in the Harrow, Hasselbalch, and Lloyd algorithm for solving linear systems of equations. So this leads to the second part of my talk, which talks about linear systems and data fitting. So the linear systems algorithm really actually is built out of three components. And the first component is quantum simulation. The second is it uses essentially ideas from phase estimation and amplitude amplification in order to make everything work. And basically the way that this problem works is imagine you have some known matrix A multiplied by some unknown vector. It gives some known data. And what you want to do is you want to find the unknown vector. So this is a standard matrix inversion problem that you want to solve, something that people do all the time. So obviously, if this actually provided an exponential speedup that has no caveats, this would certainly be a killer application. But there are some pretty big caveats that we'll get to in a second. The way that that you approach using quantum computers in order to solve this problem is you begin with a basic problem, and then you quantize it. You replace the input vector by a quantum state. And again, this quantum state, because of normalization, will only be proportional to that input state. You can lose constants of proportionality with the way that they design this. Then what you do is you invert A by diagonalization. And the way the diagonalization works is basically it uses phase estimation to store the eigenvalues of e to the minus iat in a register. Then you divide by the eigenvalues in order to implement E inverse. And that's how the quantum algorithm essentially does its job. And the key point, though, is that at the end of the algorithm, what you end up with is you end up with a quantum state that encodes the answer to your problem, not the answer. And that's a big drawback, because in general, the size of the problem is exponential. So if you wanted to read the output out of this, you'd have to sample the quantum state an exponentially large number of times. And you would totally lose any advantage that you could possibly get from this algorithm by doing so. So that's one of the major drawbacks of this particular algorithm. However, you can, if you're interested in this, I don't know why you would be, but what you can get out of this is you can figure out expectation values of your solution to the system of equations. There may be some application where this is useful, but I don't know what it is right now. And furthermore, this work can be actually applied to solving systems of differential equations, but again, you don't get the solutions there. You can only find the expectation values or other similar properties to systems of differential equations, which, although I've got to admit, does have some value there. It doesn't give you quite everything that you'd want.
But one case when y is a sequence of zeros and ones.
Yes.
So then, when you compute ket lambda, you should know lambda. No?
I'm sorry?
So if lambda,
so let's go back here. I think this
it's a
might
binary problem, don't you get later
right,
back out?
the binary case.
Oh, okay. So if you get you'll always get a binary representation. But the way that actually this is encoded is, generally speaking, it's going to be all these real values for each of these components will be encoded as amplitudes of the particular values of this. So, for example, the first entry in that would be encoded as the amplitude. Yeah.
There is an sufficiently important case when y consists of zeros and ones. So the amplitudes are sort of
right, but the
0 or 1.
Yeah, the amplitudes will be 0 and 1 in that case. And in that case, you may be able to take advantage of the peculiarities of that particular constraint to learn more information than you would otherwise. But certainly the general problem is going to be hard. Maybe this particular problem that you mentioned, there could be a cunning way to get around it, but I don't know what that is for the moment. So there's two basic problems, I guess, for this. We mentioned the output problem of reading the output, but also the input could be exponentially hard to generate. So you have this really odd situation in a way with this algorithm, right? The actual hard part on a classical computer now becomes trivial, but generating the input and reading the output becomes extremely hard. So,
well, I guess to be fair, it would be extremely hard on a classical computer.
It'd be extremely hard on a classical computer as well.
Yep. Right. Once you load it once, it doesn't get destroyed the first time.
Exactly.
So you have to exponentially reload it to
Yeah.
get the accuracy you want back out. That's the real problem there.
So clearly, this isn't a killer application at all. The question is, is there something that you can do with this? Can you generalize these ideas to come up with a different algorithm that doesn't have these same drawbacks? And this is something that Daniel Braun and Seth Lloyd and I thought about when we were approaching this. And the application that we thought of was quantum data fitting. And the basic idea behind the problem is as follows. Oh, sorry. Data fitting, to me, is such a ubiquitous task in general purpose computing that if we did get a quantum speedup for this, then certainly this would satisfy the goal of this talk. It would be a killer application for quantum computation. And so the question is, well, does it work out? Well, let's discuss the data fitting problem and how that actually works. Imagine you've got some function, a y of x, and what you want to do is you want to represent this as some combination of fit functions, fj of x. Your goal is to find weights for each of these fit functions that minimize the square error. So that's the idea. And there's many ways that you can do this. Conjugate gradient methods are a great way of doing this on a classical computer. But you can also use a linear algebra approach where you just apply an operator known as the Moore-Penrose pseudo-inverse. And that operator is given down here. The key advantage of our method, even though this is actually more complicated than the inversion problem, is that this matrix F here no longer necessarily has to be square. So, for example, you could try to fit an exponentially large data set to a line. Right? In that case, your output dimension would be, you'd have 2 parameters to fit a line. So in that case, you could actually solve the output problem. You could efficiently read all the information that you need for sure in this one particular application. The input problem still remains, unfortunately, but the output problem could be resolved by this application. All you have to do is apply this Moore-Penrose pseudo-inverse. I should also mention that the pseudo-inverse operation, in the case where the matrix is actually invertible, reduces to the previous problem considered by Harrow, Hasselman, and Lloyd. So the way we do this, we follow the exact same sort of strategy that Harrow, Hasselman, and Lloyd employed. You start with your vectors and you encode them as quantum states with each of the coefficients stored as amplitudes of that particular value. So, or I should say entries. And then what we do is we use a trick, because in order to leverage quantum simulation, we need to have a Hermitian matrix. So we need to have something that is self-adjoint. And that generally won't happen for these fitting problems. So we use a dilation of the space. We introduce an additional qubit in order to make the matrices Hermitian in a larger dimension. And after using this trick, it turns out that this f dagger f inverse is actually just f inverse squared. So after using this trick, this ends up becoming that. And so this can actually be employed or executed by using the Harrow, Hasselman, and Lloyd ideas 3 times.
Did you say qubit? Is that 1 qubit?
Yeah, you actually only need 1 in order to extend it out. So the idea is as follows. You generate the initial data. Then you use Harrow, Hasselman, and Lloyd to implement f dagger. I should say you don't quite use it because you don't need to divide by the energies in that case. In that case, you multiply by the energies, but everything else is exactly the same. Then you use the algorithm 2 more times in order to implement these f inverses. And that's what you do. The cost of doing so is as follows. The key points take home is that it's efficient. There's nothing that's exponential in this problem. S is the sparseness of the matrices in question. Kappa is the condition number. And epsilon is the error tolerance. So that is, and capital N is the dimension of the largest dimension of the matrix F. So you can do a number of things that are actually kind of interesting with this. So yes?
How are f dagger and f inverse related?
How are f dagger and f inverse related? Okay, they are not directly.
It's Hermitian.
But if it was unit, you're thinking unitary.
Yeah.
If they were unitary, then f dagger and f inverse would be the same. But in this case, the
It's not square.
it's not square.
Okay.
So this is just the conjugate transpose of a rectangular matrix.
Okay. No, because I said normally this whole thing just collapses down to then an f dagger cubed.
Yeah.
Will that work in the square case? Does it help you at all? No, because you could do the whole point was the Penrose pseudo-inverse.
Yeah.
Okay.
Exactly. The whole point was to use a more Penrose pseudo-inverse in order to write this as a series of matrix multiplications that you can then carry out on a quantum computer. So that's the basic idea. And there's actually a few things that you can do with this. Although the output state, in general, could be exponentially large. And it could be, for the fitting problem, hard for you to actually learn to fit. It turns out that you can actually learn the quality of the fit efficiently, regardless of the dimension, which may come as a surprise. Also, of course, if there's a small number of fit functions that are being used, you can directly learn the fit.
Don't you still need an oracle here then for your fit functions?
OK, so I haven't mentioned two oracles. So there's two oracles. Well, actually, no, effectively, there's one oracle, sorry. The oracle will provide you, all the matrix elements you need for the fit functions in a particular basis. Or, in fact, in general, you can imagine it in several bases if you have different natural bases for each of the fit functions that are used there. It's also useful to imagine that the input state is generated by an oracle. But
so are the oracle costs in this?
Yes,
value?
actually, yeah. These costs that I mentioned are effectively the query complexities. So the way that you would go about and learn the quality of the fit is really straightforward. What you do is you'll note that f lambda is gives you the approximation to the data set that you have. And y is the precise data set you have. So if you want to compare the two, just use a swap test. The swap test is a quantum mechanical test that allows you to efficiently determine the difference between two quantum states. So you repeat this process some number of times, and then you end up finding the quality of this fit by comparing. So one of the things that's actually kind of interesting is actually the cost of this algorithm is less than the algorithm I gave previously. The reason why is because the f here clobbers one of the f inverses that was used in order to construct lambda. So actually making f lambda is cheaper than making the previous state.
Would it pay to do amplification in between there?
Very good question. So there's only one step using our approach that it actually pays to do amplitude amplification. Let's go back. And this is where the capita of the sixth comes from. This is the only step that we use amplitude amplification in. These two steps over here, it turns out if you try to use amplitude amplification after that, you have to reflect around the evolved state, and it's just too expensive. It's the cheapest thing to do is just use amplitude amplification here and not use it on those two.
Something that was, if f is not square, what is f minus 1?
Excellent question. So f here, sorry, is what I should be saying here is that these are not the rectangular matrices in the original problem. These are the Hermitian extensions of the original matrices. Okay? So from this perspective, once you've dilated it to a Hermitian matrix, f inverse of that dilation makes sense.
It is square.
And it is square.
But f dagger is not f inverse.
F dagger is not f inverse.
Because the Hermitians are not unitary.
Yeah. And OK, so the next thing is if you also want to learn the value of the fit functions, well, one of the things you can do is you can just use compressed sensing as a tomographic technique in order to learn what the amplitudes are for the output states. And that cost ends up coming in as this additive term here, where m prime is the number of fit functions that you actually use, and epsilon is the error tolerance. Another thing that I should mention that's really kind of cool that you can do with this is that you can actually find, if you don't know a priori, a good set of fit functions actually by measuring the output of the algorithm. Because the way that everything is encoded, it encodes the answers as amplitudes. So the functions that have the highest amplitude are the ones that are most significant to the fit, and they're the ones that you're most likely to measure when you measure the state in the end. So what you can do actually with these algorithms is something really kind of cool. You can say, all right, I don't have any idea what a good set of fit functions would be to represent this data. I'll start with a complete or near complete set of fit functions. Then you measure the output state, and you sample from that. You find the ones that appear most frequently and cut out all the rest of them. And that will give you, in some cases, a good guess for a set of fit functions that you should use for the problem, even if you can't a priori know which fit functions are best.
But I still have the classical cost of doing tomographic work.
But the thing is, you only have to do the actual tomography later, right? Once you've found the fit functions that you want to use in the final tomography, then you do the tomography. So this process over here you can think of as like a compression process. You start with a set of fit functions, and you use this to throw out the ones that aren't useful. So just to compare to Harrow, Hasselman, and Lloyd, preparing the initial state is inefficient with Harrow, Hasselman, and Lloyd's approach. Unfortunately, with quantum data fitting, the same thing in general is true. Learning the output isn't necessarily a problem with our data fitting algorithm in many cases. And furthermore, we can actually estimate the fit quality efficiently. So which gives you actually something that's useful that you can do directly from this particular application. Also, going back to something that I mentioned previously, a very natural application of this is parameterizing quantum states. Because if you have a quantum state that's yielded to you by an algorithm or some other device, then you've already solved the input problem. You can just use this as an alternative to tomography and get an approximate reconstruction of the quantum state that way. And yes, unfortunately, it also strongly depends on the sparsity of the matrix in the basis that you choose for the problem. So you really do have to be clever about the way you choose it or use good simulation methods. So is data fitting a killer application? Well, I honestly have to say I think no. The reason why is because of the fact that it still has many of these problems that the Harrow, Hasselman, and Lloyd algorithm had. In order to be a killer application, what I'd love to be able to do is get some random data set that somebody has and just feed this in and get it to process that random data set incredibly quickly. The problem is, if you have to generate that data set via a lookup table, you're not going to be able to prepare that initial state efficiently. So what that means is that this can't be used in order to solve many general purpose problems that people are interested in. But it comes agonizingly close. Maybe there are particular problems that people are interested in, maybe in a cryptographic setting or something else, where the initial state actually can be efficiently prepared. And I think that taking a look at studies along these lines may actually end up leading to the first true killer application for quantum computation. Thank you very much.
I think it's, let's think of a time where all the big data in the world will be stored as quantum states to begin with. Yeah.
Yeah, if it's already at a point where, you know, where your resources are already quantum, then I agree with your remark.
So do you have examples of problems where the state preparation is efficient?
Well, yeah, actually, I do have problems. And this, of course, betrays my background. But imagine what you have is you have a untrustworthy quantum simulator that produces, you know, some particular output data, and you'd like to learn what that data is. Well, then you can use that device to generate your input state, run it through this algorithm, and then fit it and learn the fit quality efficiently. But however, yeah, I think that there still is more work that probably should be done. One of the things that that we haven't done is we haven't looked at particular sets of fit functions that can be generated or cannot be generated efficiently. And that would probably be sort of the next step towards making this much more practical by identifying some problems that are concretely useful for people to solve and actually looking at the costs of, in particular, implementing the oracles needed in order to perform this.
I want to note that comparison to VisiCalc is somewhat unfair in the following sense. It was pretty obvious that it is a step in the case of VisiCalc. It's a step toward universal computing. People like Bill Gates, who went to try to build a personal computer, of course thought about various applications, it was obvious to them that it will work in general, universal. Now here we're still in the stage that even if these are two killer applications, both of them, it's still a specialized device of the smart computer, which does few special tasks far removed from universal.
So your question is, so I'm trying to parse your question.
Is VisiCalc a reasonable thing to be comparing against for the general case?
Yes.
Well, I think it is a reasonable. The spirit of VisiCalc certainly is a very reasonable thing to compare against. In that, really, ultimately, what I'd like out of a general purpose killer application for quantum computation is something that really gets a bunch of people who already have substantial data processing needs to say, wow, I really could use a quantum computer should it ever come out in order to handle my daily problems. And I think for many of these people who aren't already in the scientific community, one of these applications hasn't come out yet.
So 3 comments. One for you, I would say view it as a cloud service. No one's going to have the machine in their office. But could you sell a service that did their data analysis much faster, much better for a general case, which is the movement direction? It's not that it's there.
More and more specialized services.
Well, I don't know how specialized it has to be if you actually solve the killer app problem. That's the point. It should be general in the end. So the two, are you familiar with Ventura and Martinez's work on quantum associative memories?
No, I'm not.
Okay. Late 90s, just a side note. Extremely efficient preparation of lots of data into states and in a circuit model. And it might be worth looking at for some of the preparation problems.
Yes.
The other is Clater, Jacobs, and Sprouse's.
I'm very familiar with that.
Okay, as I figured.
So that work in particular, I feel that some of the ideas can be used in order to speed this up. In particular, their ability to avoid using amplitude amplification and measurement in the early parts of the procedure ought to be able to be useful for reducing this dependence on the condition number in particular. I suspect that we might be able to reduce this as low as kappa to the third by adapting their techniques. But yeah, that's actually ongoing work right now that we're looking at to optimize these.
And have you thought at all about the fitting functions to actually implement the Oracle process?
Well, again, it really depends on the fitting functions and the basis in which you want to do this in. I haven't thought of it in great detail. I know that this is actually a very real and very serious problem. But I think to some extent you need to have an idea of what you'd like to use this algorithm for in the first place in order to do that. So that's what we're doing right now. We're trying to think about what the actual best use cases are going to be for our algorithm and then attack those. However, natural candidates for these sorts of fit functions would be, for example, bounded polynomial functions that only end up having support over small areas, or trigonometric functions. Those are the sorts of things that are certainly would be very easy to do, either with a quantum Fourier transform or directly using a sparse representation.
I think that would, I'm just agreeing with you, that would be a reasonable approach, because the machine learning people only pick the fitting functions they use because they're easy to compute and are easy to separate. And which are the same things. You find things that are quantumly easy to do. It doesn't matter what the actual function is so much as it has the attributes.
Right.